might start recording now, and we can do this. Are you guys seeing my iPad? I have it on my screen. Can you guys see it? The share screen?
Can.
Is that a yes or a no? You
Yes.
Okay, thumb up. Okay, thank you. All right,
Yes.
So we're in chapter 12. So moving along from 161. I know you're asking about, someone was asking about reviews. I was looking through, I did find a like a review session on mastering. I can assign that. I'll put it as optional, so you don't have to do it for credit. But if you're looking for a refresher for 161, I'll put a refresher on the homework. So, and it's going to be optional, so you don't have to do it if you don't want to. But if you and it's easy for me to always add more homework. So just let me know if you want more. But and I'll make it optional, so you do not have to do it. But anyways, we're in chapter 12. So if you remember from chapter 11 where we left off, we're talking all about like structure of compounds and that kind of thing. And now we're going to talk about intermolecular forces and what those structures, what that has on matter. And chemistry, definition of chemistry is the study of matter and its changes. So when you study chemistry, you're studying matter and you're seeing how it changes or does not change. So before I get into that, let me talk about the internet and the intranet. I'm sure you've heard of the internet before. I mean, we're talking on the internet right now. So, but how about an intranet? So has anyone ever heard of an intranet before? It's also funny, internet is actually capital, so you should always capitalize internet. It's a proper noun. So an intranet is a network. It's within a network. So maybe you've noticed something if you're at school and the internet can go down. So you lose the internet, but you can still go to the library page and renew your library books, or register for classes and that kind of thing, because the intranet, the within the network, it's still working. But the internet, so between different networks, so you can't if the internet is down on school, you can still go within Hawaii EDU, but you cannot go to like Instagram. So because the connection between the networks is no longer there. So with the same idea, that's how computer networks work. Let's talk about intermolecular forces and intramolecular forces. So intermolecular forces, these are forces between molecules. So inter is between, intramolecular forces within the molecule. So which one do you think? Which one is stronger, intra or inter? The intra, the within the molecule. Was that?
Intra.
Yes. Very good. Yeah. So if you're wondering, I guess I'm telling all my teaching tricks. Supposedly, if you ask a question, you're supposed to wait. Well, you can answer right away. I'm supposed to wait 4 seconds before I move on to let you think about it. So if you wonder if no one answers within 4 seconds, I'm just going to move on. So, but thank you, Dan. Intra is stronger, significantly stronger. And to show you, here is a water molecule. So I mean, drawn its Lewis structure with the oxygen and the 2 hydrogens. So the distance between the oxygen and the hydrogen within the molecule is 96 picometers. And for liquid water, there is, on average, between the molecules, there's a distance of about 300 picometers. Pico is 10, why isn't this? 10 to the minus 15 meters. So pico is that, so 300. So 300 is going to be 3 times 10 to the minus 13 meters. So really, really small, of course. But and those of you who had me in Chem 161, sometimes I say, hey, molecules are a lot like people, and one of the ways that we describe like friendships and relationships is we say that they're close. And you say like like my wife and I are really close, or this is a close friend. And it literally, and we describe it with proximity. So if I say I'm close with my partner, that means that we're disgusting. We're like right here together the whole time. If I use it, my close friend, you're like, come on, look, see, he's a close friend. I have my arm around him because we are, proximity wise close. So same thing with molecules. The more strongly bound they are, the closer proximity they tend to be. It's not a smooth curve, but it works pretty well. So same idea. So the oxygen and the hydrogen within the molecule are very tightly bound by how close and indicated by how close they are. But between the molecules, there's an attraction, but it's not nearly as strong as the intramolecular force within the molecule. And also water is a polar molecule, if you remember, which means that there is a negative end of the molecule here and a positive end of the molecule here. For the hydrogen, the hydrogens have electron density taken from them. So there's a much larger amount of electron density around the oxygen atom than there are around the hydrogens. And so the electron clouds, remember, electrons are like this fuzzy kind of gas, and then the electrons flow towards the oxygen. They still, partially exist, and still, greatly so, but just more the electron density is around the oxygen. So you have this buildup of negative charge around the oxygen, and then you have a buildup of positive charge around the hydrogen. It's more that the electrons flow away from the hydrogen. You have the positive nuclei, the protons that are there, the nucleus of the hydrogen. So the proton is less shielded by the electron cloud, and that's where the negative charge comes from. The other thing by partial, so when I say partial, and this is the Greek symbol, lowercase delta. So this is capital delta. This is lower delta. Lower delta means partial for science and math. The partial implies it's going to be less than 1.6 times 10 to the minus 19 coulombs of charge. So that's the charge of a electron and proton, respectively, negative for electron, positive for proton. And so that charge is a partial charge, meaning it's less than the full charge of the proton or electron. And sometimes we just say +1 or -1 because that's just, like relative to each other. But that's the SI units for charge. So that's a partial charge. Okay, so there's that with water. And so you can see then there is a bit of difference between oh geez, my Apple Pencil, not my Apple Pencil. There's a difference between inter and intramolecular forces. So let's move on and talk about states of matter. So solid, liquid, and gas. So and the way we can describe a solid is defined by a defined shape. I'm charging my Apple Pencil, my iPad, but here's my cell phone. So this is a solid, right? This has a set shape and has a set volume. The volume of this is about, I don't know, 25, 30 milliliters. And it's a little thin, well, not thinner than others. So 25 milliliters of volume, and the shape is this, rectangular prism-ish shape, right? So, and it's a set shape. It doesn't change. I'm moving it around, and the shape's not moving. So liquid, here is a glass of water, right? So the volume of this is probably about, I don't know, 300 milliliters. So if I take, maybe I'll take the same volume, I'll take a 30 milliliter drink. And so now I swallowed it, and, the shape of that, it went from like, sort of cylindrical hockey puck shaped to, my esophagus shape as it was going down. Now it's the shape of my stomach, or at least, probably the bottom of my stomach, right? So, well, I guess it mixes with the acid and the cereal that's there, right? Anyways, the point is that liquids do not have set shapes, right? So the volume does not change, but the shapes do change. Well, I guess I should also say, just to be exact, the shape and the volume so for solids, the shape and volume don't change that much. So if you look at things under a microscope, like my glass right here, although glasses can be shown to be slow moving liquids, but it's more or less behaves like a solid. if I squeeze the glass like I'm doing now, and if you were to look at it closely, actually I am deforming the solid a little bit, but it doesn't deform that much. I mean, generally speaking, the shape does not change. I mean, yes, it can change a little bit, but I mean, generally speaking, the shape stays constant. Same thing with liquids. The volume stays the same. The volumes can change a little bit with liquids. So if you compress them, they'll compress, for instance, but they really they don't change that much though. But also the fact that liquids are said to be incompressible. I mean, they are compressible, but not very compressible. That's how hydraulic lines work. So like your brakes on your car, that's how they work. You ever notice that your car brakes work even if the car is off? And the reason is because so the way the brakes work is when you push on your brake pedal, it's a hydraulic line. You push on it and it applies pressure alongside the brake line, which is it's a tube full of brake fluid. And then it goes to your calipers. And the way brakes work, you have your brake pads and the calipers squeeze on the brakes. And that's the hydraulic action from you pushing your foot down on the brake line. And that all works as long as there's not any air in the line. So, and then we go on to gas. Air is a gas. So, which means it has neither set shape nor set volume. And gases just fill whatever container they're in. So like if I took like my tire from my car and say, hey, what's the shape of this tire? And you're like, well, it's like, or the air in the tire. Like, well, it's kind of this, I don't know, is it called a bunt? Is that what's called the tube donut looking shape? It's like, oh, it's that, tube donut bunt shape. And if I were to like slash a tire and like, all right, what's the shape of the air now? Like, well, it's the shape of the room. The air just went and filled whatever container it's contained in. So, and so gases have neither set shape nor set volume. And that comes back to the brake lines. So if you have air in your brake lines, what happens when you push on your brakes? Nothing happens because you take that hydraulic force and it goes in the gas and just compresses the gas. Whereas liquids are not very compressible. In fact, they're said they're incompressible. Like, not really, but they are, for all intents and purposes, they are incompressible, especially for hydraulic lines. It carries the force through a hydraulic line. So gases, though, do not. Okay, so what about intermolecular forces? Solids, relatively speaking, solids have relatively strong intermolecular forces. So meaning, and when you have them together, they don't move that out. Oh, I'm at home. I forgot. I can use ice cubes. I'll be right back. I guess I could do this at school too, but I just always forget. So water is weird. I'll talk about water in a couple of lessons, but water is strange because we're so used to seeing all three states of matter of water, right? I mean, not everyone. I mean, I'm used to seeing solid iron. I've never seen liquid iron. I've certainly never seen iron vapor, right? So I mean, it's very rare to see all three states of a specific compound or elements. So here's ice. This is solid water, right? And actually, I can feel it right now. It's melting in my fingers. It's getting slippery. So what's going on right now is the water molecules, and they're kind of like, I'm going to drop it in my water because I don't want my table to get wet. So they're like a V shape. And so here is solid water. It's the molecules move around. So remember, temperature, if you remember from last semester, temperature means average translational kinetic energy, meaning, so here is ice and the water molecules are just, they're stuck in space. So solids mean set shape. So the water molecules are moving with temperature. They're not moving that much. As I'm holding the ice cube, as I was, these are getting hotter. They're moving faster. And then you get to a point where the water melts, or the ice, I'm sorry, the ice melts. So what happens when the ice melts? Now it becomes a liquid. Now the molecules are more free to move. So they're not stuck like a solid. Now they're free to move, but they're still relatively close to each other. So now they're liquids, you heat it up, it gets hotter, hotter, hotter. And then you get to the point where then it vaporizes. So what happens? What's going on with this? So melting point, when you're melting something, you're breaking intermolecular forces. You're breaking forces between the molecules. you're giving the compounds enough energy such that it's going to break the intermolecular forces. And then we have this medium state, the liquid state, and liquid states are, they're not always present. So, but liquid states, it moves around a bit. They're still kind of together. But then if you get enough energy, then it turns to vapor. Vapor is where there's the molecules have some, or atoms have so much energy that they just don't, they're not attracted. They just fly apart. So from that, the strength of the forces between atoms and our molecules, atoms for like elements like iron or platinum. So the strength of the bonding that holds them together, one of the indicators is the melting and boiling points. So the higher the attraction, the higher the melting and boiling points will be for elements and compounds. So, and it's related to these intermolecular forces. And we also talk about, so the solid and liquid is referred to as the condensed phase. So if you hear someone say condensed phase versus vapor phase, we kind of loop solids and liquids together into the condensed phase. And this is probably more for stuff like astrochemistry. And the reason being, so if you look at the density of things, right? So you compare air and water. So generally speaking, air has about 1,000th as much matter as liquid water. Like I like to swim, right? And I'm in water, I can swim, and I'm pushing water with my hand, I'm propelling myself forward. It's really easy. I can do, like a breaststroke and push myself forward, or, front crawl and really push myself forward. I'm doing this with air right now, and I can kind of feel a little bit of wind on my face, right? I am not being propelled forward by waving my hands like this, right? So that's doing absolutely nothing. And why is swimming in water, why is that propelling me forward? And why is, swimming in air just absolutely worthless? Because I'm pushing 1,000 times as much matter when I'm swimming in water. And so it's just, that's just, a lot more matter. And if you look at like basalt, so basalt has a density of around 3 grams per cubic centimeter. Water is 1. So basalt rock has about 3 times as much matter in it than liquid water does. So you can see that like solids and liquids, I mean, within the same order of magnitude, they're about the same amount of material, within a factor of 10. Whereas gases, air is like 1,000th that. I mean, that's not, I mean, it's not that at all. So we call the solids and liquids condensed phases. And okay, let's talk a little bit about the, I guess I mentioned some of this already. The forces, the force between two molecules, it's the Coulombic force. So if you have taken general physics before, we have the 4 fundamental forces being gravity, electrostatic, nuclear strong, nuclear weak. And some people include a 5th force being dark energy. But it turns out nuclear weak is actually electrostatic. So there could be 3 forces. So it's, anyways, the attraction between molecules is electrostatic. So electromagnetic, however you want to call it. And so it's Coulomb's law. Coulomb's law is written right there. The force is equal to a constant, 1/4 pi times the permittivity of free space times the charge of 1 charge a second divided by the distance between the charges squared. So that's the Coulombic force. So which means that the so what is the greater the charge, the greater the attraction or the force, or the smaller the distance, the greater the force, or the smaller the charge, the weaker the force, or the greater the distance, the weaker the force. So that tells you a bit of what I also said before about things being closer means they're stronger bound because of that, the distance as well. So, and of course, the charges are going to be less than the charge of a proton or electron respectively, because they're partial charges from the electron cloud. So these are considered to be relatively weak compared to covalent bonding or other types of intramolecular bonding. So how are we doing so far? Questions? All right, moving on, let's talk about the different types of forces. Let's start with the weakest one. So the weakest one are called London dispersion forces. Sometimes they're called London forces, sometimes they're called dispersion forces, sometimes they're called London dispersion forces. So We actually use all three interchangeably. So, and these are induced dipoles. So let's talk about a noble gas like xenon. So xenon is a noble gas. It tends not to bond with things. And so in atoms, more or less, they're very spherical. So they're very spherical. And if you take two xenon atoms close to each other, what happens is that as this xenon atom is approaching the other xenon atom, they have a negative electron charge, right? So actually, as xenon atoms are moving in space, and when atoms approach each other, they actually slow down. And the reason being is that the negative electron charges, there's a repulsion, and your kinetic energy then turns into potential energy, and it slows down. And if they fly apart, then they turn back into kinetic energy. But as they approach each other, what can happen is this electron cloud can push on this one, and this electron is like, oh, I don't like this negative charge. I'm going to go this way. So, and as this electron cloud deforms, it actually, so as it deforms, the nucleus becomes a little bit more exposed, and you get a partial charge. So the two atoms, one will kind of induce a dipole in the other one. And now when the dipole is being induced, you have this really weak attraction. Now there's an attraction here between the xenon atoms. And so we can have solid xenon, we can have liquid xenon, but it's not a very, it's a very low melting point, very low boiling point. To give you an idea, we can look that up. Where is my periodic table? I love this periodic table. Xenon. The melting point is negative 111.8 degrees Celsius, and the boiling point is negative 108 degrees Celsius. So you can see there's not much of a liquid phase there for xenon, at least at 1 atmosphere. So you can see, I mean, that's considered low temperature, not surprisingly, right? I see negative 100, I'm thinking that's cold. So it's low temperature means low kinetic energy, right? So it doesn't take a lot of energy to break these xenon induced dipoles. So okay, so that's where the induced dipole is. That's where that's the nature of the London dispersion force. What else can change it? So what tends to have higher forces is the bigger size. So size and or molecular weight. So hydrocarbons, for instance, they have quite a bit of, well, that's where their primary intermolecular forces are, London dispersion forces. So hydrocarbons, the heavier they are, the more forces. So if you look at something like methane that has a molecular weight of has 16 grams per mole, methane's a gas. Whereas gasoline is a liquid that has 118 grams per mole, gasoline, so it's like a liquid, right? And then you can have things like paraffin wax, which is going to maybe around 200 grams per mole, and it's a solid. So you can see that the bigger the hydrocarbon, the heavier it is, the more forces it's going to have. But in a hydrocarbon is a molecule that has hydrogen and carbon in it only. So you can learn about that more in organic chemistry. So, but if you look at the noble gases here, helium is the smallest one, and then as you go down the periodic table, the atoms get bigger. Since they're getting bigger, the bigger atom means bigger electron cloud, which means it's more polarizable, meaning it's easier. So if you have I guess I only have one set of hands, right? But if I make a really tiny fist and I have this electron cloud's really tightly in there, it's not going to move as much. But if I have this big electron cloud, it's actually easier for this electron cloud to flow. And that's a phenomenon called polarizability. It's easier to polarize. It's easier to create, poles, and therefore greater dispersion forces. So the other thing is the closer the molecule is to a sphere, the weaker the forces, or the more flat it is for hydrocarbons. The more flat the molecule is, then the higher the forces. So to give you an idea, let's say I'm on my tabletop, you know, I guess I can't show you, I guess I could, but I'll use a book. So you have a flat surface. This is a book that I'm reading right now. And let's say I put a softball on here. So, and if you know Velcro, so what if I put one type of Velcro on the book and on the softball, I put the other type of Velcro, and I can tell you it's going to stick. So let's say instead of a softball, I put a plate, you know, so I put a plate on here. Instead of a softball, I put a plate. And which one's going to have more attraction? And the answer is obviously the plate. Why is there more attraction? Well, because this, for the sphere, for when you have a sphere on a surface, there's a very little bit of contact there. If I have something flat, it's going to have a lot of contact. So same idea, when you have two flat surfaces together, there's a lot of contact, a lot of space for the electrons to interact. So remember, electrons hate other electrons, they're negatively charged. So electrons love protons, they're attracted to net positive charge, and they don't like negative charge. And around molecules, there's the electron cloud. Every single surface of a molecule is negatively charged. So as they approach each other, there's repulsion, right? That's why, I mean, besides the whatever the Pauli exclusion principle, I mean, I'm pushing my hands together. They're not overlapping, right? They're repelling. It's from the electrons in my electron clouds are pushing back from each other. So that the greater contact, this means there's more interactions between the electrons. Therefore, there's more polarizability going on. Whereas you have two spheres, the contact between the spheres is not that much, and therefore the polarizability goes down. Okay, and I mentioned before about molecules that if you have a higher melting point or higher boiling point, that means the higher the boiling point, the greater the attraction. So if you see, here's neopentane. Pentane means 5 carbons. So if you see here, here's neopentane. You have a carbon in the center, and you have 4 methyl groups, so it's 4 CH3s around it. And so this is going to be a tetrahedral shape. So it'll be a tetrahedron of tetrahedrons. So it'll be a tetrahedron shape with 4 other tetrahedrons. So it's going to be kind of spherical. Then you have normal pentane, and this is just going to be a straight chain. So this is a relatively flat molecule. So straight chain molecule, and there should be, with that logic, as I just mentioned, there should be more attraction away from the spherical shape. So the spherical molecule should have low attractive forces, and the linear molecule should have more attractive forces. Therefore, we should see higher boiling points for the normal pentane and lower boiling points for the neopentane. And that's exactly what we see. So we see the boiling point for neopentane being 9.5 Celsius and normal pentane to be 36.1 Celsius. So how are we doing so far? Questions? All right, so moving on, we've covered London dispersion forces. Let's make these forces stronger. We started with the weakest. Let's go for the next highest, and it's dipole-dipole. So also known as permanent dipole. So you have induced dipoles. So you have, I mean, you can't get any more neutral than a xenon atom, right? It's just an atom. So xenon atoms are neutral, but then you have molecules like water, but we'll get to water later. Water that have poles on them, they're polar molecules. So hydrochloric acid or hydrogen chloride is an example of one. So you have, with the molecule, you have that electron density. So the electron density tends to go more towards the chlorine. So it has a covalent bond, but it's a polar covalent bond, meaning it's unequal sharing. So the chlorine takes more than its fair share of electrons. Well, it's just the chlorine atom has a +7 nucleus, and hydrogen has a proton, right? So it's just 1. And so the electrons, they're like, you know what? I like the +7 charge center better than the +1 center in hydrogen. So I still like you, hydrogen, but I'm going to just, because I can be in many different places once because I'm an electron, I'm going to be around the chlorine more. And because of that, the chlorine atom gets a lot of negative charge around it, and then the hydrogen has less. And why doesn't it just rip off all the way? Well, it's I mean, also don't forget electrons. It must be pretty pragmatic to be an electron, because electrons can literally be repulsed by themselves. So because electrons can be in many different places, and electrons don't even like itself. So if you have a free electron in space, it tends to get really big, because if it's not bound by an atomic center, and it kind of blows up, because it's repelled by itself, it has self-repulsion. And the same thing, if the electron density gets too high around the chlorine, then the electron is going to be repelled by itself, and it's going to be repelled by the other electrons. So it's an interesting dance that happens there. So there is still electron density around the hydrogen, but it's just not as much, like I said. So you have these permanent dipoles, and it turns out the charges, the partial charges on permanent dipoles are higher than induced dipoles. So it's higher than that. And then because of that, there's more attraction. And so remember I just talked about that the molecular weight, which is kind of analogous to size, meaning that the heavier a molecule is, the higher the dispersion forces. Well, let's look at two molecules here. We have ethane and we have formaldehyde. They're both about 30 grams per mole. So they're I mean, slightly different, but by only 4/100ths of an atomic mass unit. So very, very close to the same mass. The difference is formaldehyde. Formaldehyde is a polar molecule, and it has a negative end around the oxygen, a positive end around the hydrogens in the molecule. And ethane, hydrocarbon, it's pretty much nonpolar. And so because of that, there's only dispersion forces here with ethane. So formaldehyde will also have dispersion forces. So it does induce a dipole, but the fact is that an induced dipole is not nearly as powerful as the permanent dipole that's there. So because of that, we should see both higher boiling points and higher melting points for the permanent dipole, because I said it was stronger. It's stronger and because of the strength of the forces means more of a solid or liquid phase. And again, that's exactly what we see. Ethane has a melting point of negative 172 degrees Celsius. Formaldehyde much higher by 80-ish degrees, right? So to negative 92. And the same thing with the boiling points. Ethane boils at negative 88, formaldehyde at negative 19.5. So the bonding in formaldehyde is stronger than the bonding of ethane. And since they're the same mass, it's not the London forces, it's the dipole forces. Okay, so let's look at this example. Which molecules have dipole forces? So to do this, you have to remember all that stuff from Chem 161. If it makes you feel better, you really only have to know this for this chapter. So you can forget most of, like, at least the Lewis structures and that stuff. You can start to do brain drain. But which one of these have dipole forces? So you have to figure out which molecule is polar. The polar molecules are the ones that have dipole. So carbon dioxide. So carbon has 4 electrons plus 2 times 6 for oxygen. So that is 16 electrons. And you have carbon and the oxygens there. So I've placed 4, 6, 8, 10. Oh, what's one too many? 10, 12, 14, 16. I've placed the electrons on the outside. Now, carbon only has 4 electrons. It wants 8. So it takes 2 from the oxygen, makes a double bond. The other one, now it has 6. So it wants 2 more. So it takes 2 there. And now oxygens have an octet, carbon has an octet, everyone's happy. And then you look at the VSEPR chart. This molecule is linear. This is a linear molecule. And since you have the same atom on both sides, this molecule is nonpolar. So this molecule there, linear, nonpolar molecule. So that one does not have dipole forces. So that one's a no. Methylene chloride or dichloromethane. So you have 4 from carbon plus 2 times 1 for hydrogen plus 2 times 7 for the chlorine, for the halogen. Those are the valence electrons. So although I guess at this point in time, you can probably notice you could do the shortcut where hydrogen tends to bond with 1, the halogens tend to bond with 1, the carbon tends to bond with 4. So carbon is going to bond with 4, and it's going to bond with a hydrogen, it's going to bond with the chlorine, and then the electron, well, the lone pair is going to go around there like that. So if you want, I can go through the formal way with that, but I mean, that's most of the ones that you'll do with this chapter. You can just do the the quick and easy way for drawing them that way. But okay, so this is the molecule, and the structure here, this is tetrahedral. It has 4 things all bonding, so it's tetrahedral. So one of these is different. So tetrahedral is only nonpolar if they're all the same. And because of that, you're going to have a negative end of the molecule here and a positive end of the molecule here. The electrons are going to flow towards the negative chlorine molecule or atoms. And so this means this molecule is polar. And that means that yes, so methylene chloride here, or dichloromethane. Methylene chloride is the common name. Dichloromethane is the proper name. So this is that it does in fact have dipole-dipole forces because it's a polar molecule. So, and then last, methane structure, the 4 things, 4 carbon, hydrogen each bonds with 1. This is a tetrahedral molecule. So tetrahedral molecule, all of them are the same. So therefore this molecule is nonpolar. It's a nonpolar molecule. It does not have permanent dipole forces. So the only one that has dipole-dipole forces in this one is B. So dichloromethane. So questions on how to do this? Okay, let's see if you can follow. We're going the other way around. Which molecules do not have dipole-dipole forces? Oh, I guess I forgot to do this. I can make a poll. Do I have a poll? Oh, crap. I should have done this. Well, think about that, and I will make a poll. All right. Here's your poll. Let's see if you can solve it. I'll give you some time. You should see the poll going up.
Sorry, where can I find the poll?
Students are answering. I guess it should show up. Do you see it now, or? And I'll stop it after.
Sorry,
It's okay. I'm not grading you on it. All right, I'll end the poll. Here's the results. So you can see we have 2 people voted for B, 1 for D, and 4 went for C. The correct answer is in fact C. So if you look, so if you look at this, so water, so this molecule here, it's got 4 things, which means it's tetrahedral in structure, but with electronic structure, but it's bent. It's a bent molecular structure. So tetrahedral electronic structure, bent molecular structure, and all bent molecules are polar. So this is a polar molecule. So sulfur dioxide, three things, it's going to be planar electronic geometry, but since it's got a lone pair, it is a bent molecular geometry, and all bents are polar. So then carbon tetrafluoride here. So it's got four things, it's tetrahedral, and all the things in the tetrahedral structure are the same. Therefore, this molecule is nonpolar. So carbon tetrafluoride is going to be a non-polar molecule. Then you have dichloro-difluoromethane here. So again, it's a tetrahedral molecule, but in both electronic structure and molecular geometry, but they're not all four of the tetrahedral bonds are the same. And therefore, this molecule is polar. So A, B, and D are polar molecules. C is a non-polar molecule. Therefore, the C is the only one that's not going to exhibit dipole-dipole forces. So does anybody have any questions with that? Does anybody have any questions with how I went through the analysis? So this is your chance to this is me asking for feedback, and this is your chance to get extra whatever schooling on this, if you literally schooling, because we're in school, so we if you have unless I explained it perfectly and you understand absolutely everything I said, that would be awesome. If not, if you have any questions, I can go and I can show you more stuff.
Oh, understood.
Okay, awesome. All right. So let's move on and not talk and move on to talk about we're different. So we're in intermolecular forces. So we're going to move on. We're talking about a hydrogen bond. So hydrogen bond, and a hydrogen bond is it's actually a permanent dipole bond, but it's we give it a special category. So, and hydrogen bonds deal with a hydrogen atom directly attached to a fluorine, oxygen, or nitrogen atom. So if you have a hydrogen that's directly attached to a fluorine, oxygen, or nitrogen atom, the thing is that fluorine, oxygen, nitrogen are very, very electronegative, and it draws a lot of electron density to those atoms. And then the hydrogen is very electron poor. So that hydrogen is very positive, and molecules that have this, they can engage then in a permanent dipole attraction, but it's pretty strong. It's a relatively strong permanent dipole. So, and I guess I marked this molecule up. This is methanol. Here is methanol. So, and the point is that the area that have a hydrogen bond, it's going to be right here. So there's hydrogens here, but those hydrogens are not directly attached to the oxygen. They have the carbon in the middle. So if you look at this molecule, this hydrogen here, I should change my color. This hydrogen here, that one is relatively electron poor. And so that means it's relatively higher positively charged than the other hydrogens. So these hydrogens don't have much charge of any on them. They're pretty covalently bonded. There's a little bit of a polar bond, but not that much. So those hydrogens are pretty evenly bound with a carbon. This hydrogen though, is not very strongly bound. Well, it's got a lot of density away from it. And also, if you go on and talk about organic chemistry, they'll call this hydrogen, it'll be referred to as an acidic hydrogen. It'll be easy to rip off this hydrogen. So that's the acidic hydrogen. Meaning if you take methanol and you throw it in, methanol is a liquid, if you throw sodium metal into methanol, you'll make something called the methoxy ion. It's the sodium will rip off that hydrogen, and you'll have sodium plus and then the methoxy anion behind it. So, but okay, so that means though that this type of bonding can happen if you have methanol mixing with water. The methanol, this OH group, will have a hydrogen bond, and then it can interact via hydrogen bond with another molecule that has hydrogen bonding, like water. Although water will not bond to the hydrogen on the carbon. So, well, I mean, it can, but it won't, because it has a much stronger attraction to the hydrogen that's on the alcohol group, the OH group. So there is no hydrogen bond there. And so why do we care? So DNA, right? And you've heard of DNA before, deoxyribonucleic acid. So that's where we have most of our hereditary material, at least for us here on Earth. There's other hereditary materials, but a very, very large portion of the vast majority is stored in our DNA, deoxyribonucleic acid. And so, of course, the way DNA works is double-stranded, and because it has a backup, it has the coding, and we have a backup for it as well. And also, when the DNA unzips, and then you can replicate and have two identical, or you say hope it's identical strands of DNA. And if you remember, adenine will always bond with thymine, and guanine will always bond with cytosine. And why is that so? And the reason is because adenine and thymine, they hydrogen bond in 2 places. And guanine and cytosine hydrogen bond in 3 places. But the orientation of the molecules are such that guanine can only bond with cytosine. So it's the shape of it. The two can bond just fine, but if you have 2 guanines, they don't work. Same thing with 2 cytosines. They don't bond, because you have to have the 3 sites bind in a specific fashion. Same thing with adenine and thymine. It's 2 sites. So I guess guanine and cytosine are actually bound a little stronger than adenine and thymine in that way. So, but okay, so you have a hydrogen bond, and that's a moderately strong bond. But it's also, it's a intermolecular force. So it's a stronger intermolecular force, but it's not as strong as an so within the molecule, intramolecular. So it's not super strong, right? So that's a nice feature about DNA, is that if you let it sit there and hang out, it's going to stay together in a double strand. But it's not that hard to unzip. So I mean, just sitting there, it's going to stay together. But then again, it doesn't take that much energy to unzip DNA. And we have helicase. Helicase, that's an enzyme, will do that. It'll unzip your genes. And you can unzip the DNA, and you can form RNA over it to form messenger RNA for protein synthesis. And you can also replicate DNA for cell division, right? So that's a nice feature with DNA, and it comes from hydrogen bonding. So another thing about hydrogen bonding, which is of course near and dear to me with my very little bit of hair. So if you've ever curled your hair before, so maybe you've noticed, so maybe if you have really curly hair, you can straighten it. And what you're doing when you straighten your hair, you have it looks like, the pincer or whatever, I don't know, I guess it's called a straightener. Yeah, you have your straightener. It's an oven, right? And you put your curly hair in the straightener and you straighten out your hair. And what you're doing is you're heating it up. You're removing water from your hair. And then because of that, you're altering the hydrogen bonds. Same thing when you curl. If you have a curling iron, it's called an iron, curling iron. You curl your hair. You can see you can just have to pretend that I have this beautiful long locks of hair, other than my my minimal hair that I have left, right? So my long straight hair, I can then go and I can use a curling iron and curl my hair. What happens when you get your hair wet? after you curl it and or straighten it. It goes right back the way it was because you've restored those hydrogen bonds, and then the hair has its original structure. So curly hair tends to be really flat. So if you look at curly hair under a microscope, it's flat, and non-curly hair tends to be more round. So, or at least a cross section of the hair follicle is round, whereas curly people have flat hair. Actually, my hair, if I let it grow out, it would be curly. So I get kind of frizzy like around my like sideburns if I don't cut my hair. One of my cousins, he can well, two of my cousins actually, they can grow full on froze. Is the curly hair. They like when we were younger, they used to put stuff like combs and like we were at a all you can eat buffet, and they were sticking like I think it was spaghetti in their hair, and there's like all these spikes coming out. Anyways, yeah. So back when we had hair, all those good old days. But that's hydrogen bonding. So hydrogen bonding, it's a permanent dipole, but it's a particularly strong permanent dipole. So we give it its own category, and it has both biological and for some of those like hair chemistry has consequences. So I think one of the cooler ones though, I think is the DNA. The fact that adenine and thymine bond in 2 places, guanine, cytosine in 3 places. So to show you, and like why do we? That's cool about hair and DNA, but let's look at some numbers. So here are 2 isomers. Isomer means same atom but different connectivity. So ethanol and dimethyl ether, they both have 2 carbons, 6 hydrogens, and 1 oxygen. The difference is the ether. The ether has the oxygen in the center, and then the ethanol has an OH group on it. And remember that hydrogen bonding means hydrogen has to be directly attached to an oxygen, nitrogen, or fluorine. So this right here, that does in fact have hydrogen bonding. So ethanol has hydrogen bonding, dimethyl ether does not. Dimethyl ether, this is a bent molecule. It's a bent molecule, therefore it's polar. It has a permanent dipole. And this one, of course, has a bent here. It's bent in that along the hydrogen. I'm sorry, along the hydroxide group and the methyl group here. I'm sorry, the ethyl group. The ethyl group is tetrahedral, so it's going to be more tetrahedral, kind of flat. So it's a polar molecule as well, at least where the OH group is, but because it has the hydrogen directly attached to an oxygen, it's going to have hydrogen bonding. And then if you compare the melting points and boiling points, the melting point for ethanol is slightly higher, not that much, by about 20 degrees than ethanol. I'm sorry, than ether, than the dimethyl ether. But the boiling point, look at the boiling point for ethanol, 78 degrees. So that's way higher than -22 degrees. So much higher in the boiling point for ethanol. If you wonder about ether, ether is also a drug. When you talk about ether, usually you mean diethyl ether. That's like the what they used to use in the Civil War and dentists. The first, that was the original anesthesia, was actually ether. And it's diethyl ether though. So this is dimethyl ether, and if you have an extra carbon, then that's diethyl ether. That's like if you've ever read or seen Fear and Loathing in Las Vegas. That's the drug used there also, and like I said, in Civil War and before that with dentistry, the original anesthesia. That's and oftentimes just referred to as ether. That's diethyl ether. So this is dimethyl ether. And of course, at the boiling point of -22 degrees Celsius, that's not going to be very useful, at least as far as a drug, unless you're like in Antarctica or something like that during the winter. So, all right. One of these compounds is a liquid at room temperature. Which one and why? So we have formaldehyde, we have fluoromethane, and we have hydrogen peroxide. So liquid at room temperature, it means that there's going to be relatively strong intermolecular forces. And so if you look at formaldehyde, this is going to be dipole-dipole. Because, so this is a planar molecule. So three things, it's planar and one of the atoms is different, therefore it's polar. So there's a dipole-dipole. Fluoromethane here, it's a tetrahedral molecule. One of the atoms is different, therefore it's also polar. Therefore, you're going to have two, I guess I just copy it. Why doesn't want to paste? There we go. There we go. So it also has dipole-dipole forces. And hydrogen peroxide, this is kind of drawn poorly. You have to remember these molecules. They're what's known as Fisher projections. So meaning that that one is popping out of the page, the other one is going into the page. So really, if you can look at the molecule, if you want to look at it from a different way, you can look at it like this. So it's really kind of two bent molecule, the hydrogen peroxide is just kind of two bents. So this is a bent molecule. So this is bent, therefore it's polar. And because, sorry, polar is not written well, this is a polar molecule, but it has a hydrogen, it has two hydrogens, both of them here. They are directly attached to an oxygen atom. Therefore, there are two sites on hydrogen peroxide that it can hydrogen bond. And well, it can give a hydrogen bond in two spots, and it can receive a hydrogen bond in two spots, meaning that the oxygens can both receive. Depends on, if you say the hydrogen. Usually when you talk about electricity, you say the positive goes towards negative. So although that's not really the case, but the positive charge is flowed towards the negative. Well, I'm using the terminology, Ben Franklin, the founding father, he's the one that came up with it. And whenever we talk about electric flow of electricity, we talk about positive charges moving, and actually it's a negative charge moving. But if to be scientifically accurate in my speech, I have to say that the hydrogens are the ones that give the bond and the oxygens are the ones that receive the bond, because the hydrogens are the positive ones. So although it's more the electrons flowing towards the positive, but Ben Franklin didn't know that. He just guessed, and he guessed wrong. But like good people, when we make a mistake, we just keep on going with it, right? Why should we stop a bad thing that we know is wrong? So anyways, the hydrogen peroxide has hydrogen bonding. Therefore, this is the one. I shouldn't circle this one. This is the one here. I'll put some stars around it. And that's an ugly star, but that's the one that's going to be a liquid at room temperature. So formaldehyde is not, neither is fluoromethane, but hydrogen peroxide, oh yeah, it's a liquid. You can buy it at the store. Well, maybe not 100%, but you can get pure hydrogen peroxide. Very reactive, of course. So having to start questions. All right. All right, moving on. And one of the themes of at least the beginning part of this this semester, and I'll talk about it a little bit more. Water is a really weird molecule. Water has a bunch of really strange characteristics about it, and we'll talk about some of the other things that water is weird about. Water is weird, among other things, because it's got a really high boiling point relative to its size. So water is 18 grams per mole, and it has a boiling point of around 100 degrees Celsius. If you look at a hydrocarbon, octane has close to 100 degrees Celsius, and that's 118 grams per mole. So, I mean, water has a lot of attraction in itself for its size. So water has this huge amount of intermolecular forces. So it's kind of strange. And to show you versus the other, some other elements. So if you look at this graph, you have boiling point on the y-axis, and you have molecular weight, molar mass on the x-axis. And as you can see, that as the molecular weight increases, the boiling point increases, which makes sense because so if you look at the carbon family here, carbon is above silicon, is above germanium, above tin. So these molecules here, as you're increasing in size, the dispersion forces are going to get stronger. The polarizability of the electron clouds increases, and therefore you have a higher boiling point. And that holds true for the oxygen family. Same thing, sulfur is lower in mass than selenium, is lower in mass than tellurium. But then you have oxygen. Oxygen's way up there. So how did oxygen end up having to be such a huge effect? Or why does water have such a huge, odd, high boiling point? And the reason is because it can have both give and receive two hydrogen bonds. Compared to ammonia, ammonia is beneath it. Ammonia has a boiling point of, I think, around -30 Celsius. It's pretty, I mean, it's high for because it has one hydrogen bond, so it could give 4 but only can receive 1. So the ammonia molecule, the NH3, it can give 3 hydrogen bonds, but it can only receive 1, whereas oxygen and water can both give and receive 2. That extra hydrogen bond in the water network, by mean intermolecular forces network, it causes water just to have this hugely high, at least relative to other molecules, boiling point, means high attraction. So there's a lot of attraction in that water molecule, and surprisingly so, higher than the other ones like ammonia. I always wondered, part of me wonders, like with astrochemistry, because water, we're carbon-based life forms, but we're basically aqueous. There's a lot of aqueous solutions. I always wonder what would happen then if you have like ammonia based, like can you have life with ammonia based rather than water based like we are? Or I know we're considered carbon based, but what if you had ammonia as a fluid? And one of the things though about life, we're trying to learn more and more about life and where life comes from. But one of the issues, if you have liquid ammonia and you have life in liquid ammonia, there's going to be less energy, and we're not entirely certain. If things have less energy, it means they move more slowly. So just because temperature is motion, right? And average kinetic energy is temperature. And if it moves too slowly, can you have reactions that take place? So biologically speaking, right, molecularly speaking, we're teeming with activity. Lots of chemical reactions are going on, right? As I'm talking, right, and I have all sorts of things going on. I'm burning sugar. My nerves are firing. You have ions exchanging across my nerve cells. There's the neurotransmitters. I'm having acetylcholine and choline esterase destroying the acetylcholine. I mean, there's just tons of these reactions going on, and the question is, can we have similar reactions if we had an ammonia based? But we don't know, and this is some of the questions we ask. It looks the relative idea though is probably not. So we're searching for novel life away from Earth. So we're wondering what could happen. And so anyways, that's kind of a side of a more advanced topic. Okay, and let's go back, talk about intermolecular forces. So let's talk about the strongest force in terms of intermolecular forces. And the strongest force are ion dipole forces. So water has, I'm going to zoom in here on the chlorine, and you can see water is a polar molecule, and it has, the partial positive. So you have that less than 1.6 times 10⁻⁹ coulombs. Whereas chloride ion, you can see the chloride anion there, that one has the full -1 charge. The charge of this, chloride anion is, why is it go away? There we go. The charge of that chloride anion is -1 times 1.6 times 10⁻⁹ coulombs. That's a full -1 charge, full extra electron. And so because of that, the positive ends of the water molecules surround the chloride anion. And just like that, the sodium positive ions, the negative end of the water molecules surround that. And generally speaking, when things dissolve, they tend to form either tetrahedrons or octahedrons. So, and in this case, and this in most cases, octahedron. And you can look at it another way. I mean, this is shown kind of like a flower around it, like a 6-petal flower. What really happens, if you can see this, this is an octahedron. And the water molecules form an octahedron around the chloride anions. And sodium chloride does dissolve in water. You know, not surprisingly, salt dissolves in water. Another fun thing we learned in chemistry class today. And the reason why salt dissolves in water is that the attraction of these 6 positive ends of the water molecule is about equal or greater. In the case of sodium chloride, it's about equal, actually a little bit less. So it's an endothermic process. So it's actually a little less, but it's about equal for these 6 charges, or these 6 attractions from the end of the water molecules is about the same attraction than the positive sodium chloride. And we'll learn about this later. I guess I'm jumping ahead. The other reason why it dissolves is a phenomenon called entropy for disorder. So processes, if all things being the same, they will favor entropy, and dissolved salt has higher entropy, more disorder than solid sodium chloride. So, but the energetics of it are that for things dissolving, the energetics tend to be either about the same or a little bit greater. Although, like I said, because it's endothermic for salt, it's actually, salt being sodium chloride, is going to be slightly less, but it's about the same. Anyways, that's the attraction. And this is a stronger attraction. So the ion dipole, the attraction between water and the sodium ion and or chloride anion is stronger than the water attraction. So it's stronger than a hydrogen bond. So, and sometimes these are referred to as salt bonds. Salt bonds, I guess, you can see that with proteins. It's not necessarily in solution. Anyways, here you can see though that it has to do with the magnitude of the charge. Remember, Coulomb's law is constant charge of 1 times the charge of second divided by the distance between them squared. The ion has a full charge, whereas the molecules have partial charges. Therefore, the attraction is going to be stronger. So, okay, and actually, what happens in solution and the energetics of solution, this is something we are studying now. This is something we don't understand as well, and we're learning more and more about it. And and I mentioned life, and I also mentioned liquid phases. There are some things that only happen in liquid phase. So one of them is a type of reaction called an elimination reaction. That's when carbon forms double and triple bonds. So if you want to have molecules that have carbon double and triple bonds, there has to be a liquid phase. It has to do with the transition state. So as the molecule is forming, you need to have it in solution so that the solvent stabilizes the transition state. And if not, the elimination reaction just doesn't happen. So, and that's important for us. So for us as living creatures here, because we have carbons that have single, double, and triple bonds. If we had life that never had a liquid phase, if it was just gaseous or solid, there would be no double and triple bonded carbon atoms, and at least not many of them. And at least it wouldn't be, something that would consistently happen either. So it would just be like randomly by chance. So in a very small amount. And so because that life like us needs a liquid phase. So that's why we're always excited when we see like, oh, is there liquid water? Oh, cool, liquid water, maybe there's life. That's because you need that solution phase to have some of the more complex chemistry. And we're learning about it. We're learning more about it, but it's at the forefront of our knowledge right now. I see 2 minutes left. Here is the overview for today. So we have the weakest force here is dispersion. We talked about this at the beginning. This is induced dipole. Then the next strongest one is permanent dipole, where you have polar molecules that have full dipoles. And then the next one is a hydrogen bond. Hydrogen bond is a polar molecule. They exist between polar molecules, but it's a specific type of molecule. And it's where the hydrogen is directly attached to a fluorine, oxygen, or nitrogen. And then lastly, we have the ion dipole, where you have an ion attached to, well, it's going to be another dipole molecule. Oftentimes, because we're here on Earth, it's most of the time it's water, right? But you could have other liquids. You can have alcohol. Things dissolve in alcohol as well, for instance. It doesn't necessarily, but that's also hydrogen bonded. And here's the relatively strengths of them, and you can see the range. The dispersion forces tend to be that range, the 0.05 to 20 or so kilojoules per mole. And then the dipole, you can see these ranges, same with hydrogen bonding, and same thing with ion dipole. And you can see that, generally speaking, the trend is such that dispersion is the weakest, dipole is the next strongest, hydrogen bonding is a little stronger than that, and then ion dipole tends to be the strongest. So, all right, 1 minute left, or less than a minute left. Anybody have any questions? Okay, so no questions, and finish exactly where I wanted to. Oh, and the class is over. Class is over, so I will stop.